All right. So we're going to do, I just want to make sure that we all know that. So chapter 4 homework, number 10 and 12 are the ones that were requested. Let's take a look at those, and if there's anything else that you want to go over, we can. Again, I think I mentioned this before when I was going through the homework from chapter 3. I noticed that there were some people that didn't finish problems, like we started talking about it in class, and so they wrote down what we did in class and then didn't finish it. So make sure that if we don't finish a problem when we're going over things as homework, to make a note by it so that you actually do go back and finish it, right? So that you're not just like not getting points. I mean, that's the sad deal. Okay, so number 10 is not something we've really talked about, but if you've read the book, you can probably kind of figure out what's going on, but let's kind of talk it through. It says, 4 forces act on a hot air balloon as shown from the side. Find the magnitude and direction of the resultant force. So, you've heard the word resultant before, right? What does resultant mean? Everett, what do you know? What does it mean?
It's the result of 2 or more added vectors.
2 or more added vectors. And a force is a vector, right? We've been drawing them as arrows, so we know that it's a vector. It's got magnitude, it's got direction. You've got 4 vectors there, and we want to know what happens when we add them all together. So if we take like the 2 that are going in the x direction, they're opposing each other. So there's one that's going this way and there's one that's going this way. They're not really drawn to scale, but this one's like 1520? And this is 950. And so which way is the resultant of those 2 going to go? Is it going to go to the right or to the left? To the left, because the left one is bigger. Does that make sense? So you're going to take those 2 and subtract them. Is that okay? Subtract them, and then you're going to find something that goes to the left that has a magnitude of how much? Anybody have that in front of them?
It's like 570.
570-ish? I'll trust you. You can do the same thing up and down. You got 5120 going up and 4050 going down. Which way is the resultant of those 2 going to go? You got 5120 and 4050. It's going to go up. So you'll figure out how much it's going to go up. And then the total resultant, the overall resultant, it's just like from chapter 3, the stuff we were doing. You're just going to go over and find that resultant vector. Does that help a little bit? Does that make sense? What you need to do? Madison's still looking at me a little bit funny. I'm not sure what that face is. Okay, that's totally fine.
Also, the licorice tastes really weird.
I think it tastes good. All right. Does that get people where they need to go on that one? Yes, no, still processing. I'm going to go ahead and work on number 12 unless I hear anything else, hear any yelling. We okay for now? Speak up if you change your mind. Number 12 says, a dog, pulls on a pillow with a force of 5 newtons at an angle of 37 degrees above the horizontal. Okay, sure. So we got a pillow, and there's a force of the dog pulling something. I guess 37 degrees is going to be a little bit bigger, a little higher than that. Something like, that's a little too big, but whatever. 5 newtons. So these problems are very similar to the ones that we did in chapter 3. Just instead of having a vector that's a velocity or a displacement or something, now we just have vectors that are what? They're measured in newtons, so they are what? They're what? They're forces, right? They're forces. We didn't actually say the word newtons last time, but hopefully you read your book. Did you read your book? If you didn't read your book, you should start doing that. I would recommend it strongly. It doesn't take very long. It's a good little read there, okay? So these things that are measured in newtons, we're going to talk about that a little bit more today. So really all this is asking is how much is pulling like this and how much is pulling like this. Have we done problems like that before? It's the same kind of problem that we did last chapter. Okay, so you know the angle is 37, so you're going to use sine and cosine to figure out those 2 pieces. Okay? Is that okay with everybody? any other questions on homework that you would like to go over?
Can you finish solving number 10?
I probably won't finish it, but I can take you another step. What would you like to do?
I just don't know what to do after the triangle.
Okay, so did you find the y part?
Is that when you subtract those numbers?
In the y direction?
Yeah.
Yeah, so what did you get?
1070.
1070, like that, 1070. So then you have two pieces of a right triangle. You have two legs. If you know the two legs, can you find the hypotenuse?
Yeah.
Use Pythagorean theorem. Does that make sense? So that'll give you the magnitude of that resultant vector. Is that okay? And then you'll need to find an angle. And I think that the angle, because it doesn't say north, south, east, west, we can't really use that. The way that they marked it in the book was to say so many newtons or so many degrees above a certain one of the forces. And so they picked this angle here to measure. Does that make a little more sense? Do you want me to keep talking, or does that get you where you need to go? Okay. You good? Does that make, are we okay? Sweet.
I was looking at it wrong.
Oh.
Not reading it.
It's kind of a,
Makes a lot of
it's not a problem. It's not like, oh, duh. Yeah. At least it wasn't to me when I first looked at it either. So, okay. Any other homework questions before we move back to the bowling ball? Okay. Pull those notes out from last time. Do you remember last time we were talking about bowling balls? Do you remember having that conversation? We had four situations with a bowling ball. And we were like at the cusp of coming up with this big deal theory, but we didn't actually write it down because it was time to leave. You know, it's one of those things that now that we have 85 minutes for these classes, I need like 95 minutes, right? Like, just give me a little more time. So I need to get my head back in the game here. I'm going to go ahead and put my 4 bowling balls here just to remind myself real quick of what was going on. In situation 1, what was happening to the bowling ball? Can somebody raise their hand? I want to share the fun today, so I'm going to have lots of people talking. So if you're not a person that usually talks, put your hand up really high when you know something, and I'll call on you. Is that fair? There are 28 of you in here, 29 of you in here. I want to talk to everybody today. Okay? All right. What was happening in situation 1 with the bowling ball? What was going on? What was the bowling ball doing? Nayakota, what you got? It was at rest. Yes, it was. And can I ask you a follow-up question? Something that I think you have written down there. If it was at rest, what do you know about its acceleration? Its acceleration was 0. Not too scary, right? Was that okay? Okay. All right. So I want to make sure you all have this written down too. So I'm going to write it down here because I need to have it written down. And I'm going to ask one more question about situation 1. How many forces were acting on the bowling ball in situation 1? Lydia has fingers up. Is that kind of like you want to answer? Yeah. She says 2. Can you tell me what the forces were?
The floor on the ball and the earth on the ball.
Absolutely. And I'm going to be really picky, and I really want you to do this every time. So you've got the floor on the ball. I'm assuming that one was going down, right? Or excuse me, the earth on the ball was going down.
Yeah.
Earth on ball, and you're going to label them that way every single time, right? Something on ball, because we're talking about the ball here. And you've got the floor pushing up. Is that okay with everybody? I'm just kind of coming back to you. Do you remember this situation? In case number 2, who can tell me what the ball was doing or what was happening to the ball? In number 2, take a look at your picture. We're just recalling in our experience. Yes. It was being pushed. And as a result, follow-up question for you. Is that okay? Is the ball accelerating? It was accelerating. Is that okay with everybody? It was speeding up, right? Its acceleration was positive. So A was not equal to 0. Is that okay with everybody? How many forces were acting on the bowling ball in situation 2? Xavier, what you got?
3.
3 forces. What forces do you have?
The force of the floor on the ball.
Floor of the ball, which way does that one go?
Up.
Up?
The force of earth on the ball going down. And the force of hand on the ball going right.
Awesome. And then the force of the hand on the ball going this way. Okay, everybody still happy? Situation number 3. This was the weird one. This is the one where there was a little bit of dissension, a little bit of tension maybe in your groups about what was going on. What was happening in situation number 3? Abdul, what you got? Bowling ball was rolling. Rolling, rolling, rolling. We like it, right? And tell me, was the bowling ball accelerating in situation number 3? It was not. This is weird. Was the bowling ball moving?
Yes.
It was moving, but it was not accelerating. That's a big deal. It can happen. It's rolling, but the acceleration is equal to 0. How many forces? Somebody else. I'm looking for more hands, more new friends. Everyone's like, I've had my hand up every single time, Carmeling. Why aren't you calling on me? It's all you. What you got?
2 forces.
2 forces. What are they?
The force of the floor on the ball going up and the force of gravity on the ball going down.
Awesome.
Or earth on the ball.
Because we can buy Earth, we can't buy gravity, right? Yeah. All right. Last one. Number 4. Talk to me about what was happening to the ball in situation number 4. Anna, what you got?
It was being stopped.
It was being stopped. And as a result of being stopped, was the ball accelerating? No?
Or yes, it was.
She-
So the acceleration wasn't equal to 0.
It was or was not?
It was not.
Was not. Now, you were kind of hedging there for a second. Can you tell me why?
The acceleration was negative.
Correct. Is that okay with everybody? Does that make sense? So it's slowing down. So the person on the street, if you ask them what do you call that if something's slowing down, they're going to say that it was what? Decelerating, right? We don't use that. That's just like another, like, whatever. We're just going to say that it was a negative acceleration. That's all, okay? Negative acceleration. It is accelerating because acceleration means change in velocity. And there was a change in velocity. How many forces do you have in situation number 4? Have I talked to you already?
Not today.
Okay, speak.
3.
3, what you got?
Common floor on ball up, earth on ball down, and then hand number 2 on ball the opposite direction of first hand. So left.
Like so?
Yes.
Okay. And I've been a bad kid not putting vector hats on these things. Like, what have I been doing? Jeez, Carmeling. Okay. So now you're like, yeah, that's what I had written down about a week ago. Not quite a week ago, but quite a while ago. All right. I told you we were on the cusp of something big. Let's take a look at this. Do you notice anything in common in these 2 situations, in situation number 1 and situation number 3? What do they have in common? What do you notice?
If the acceleration is 0, there's only 2 forces.
There are only 2 forces. Does it have to be that there are only 2 forces? I mean, I see that. I totally agree with you. But now I'm drawing it out even deeper. Like, whoa, is that true? Could there be 4 forces and have an acceleration of 0? Can you give me an example of a situation where you might have 4 forces acting and an object has an acceleration of 0? This is kind of weird, so I want to give everybody a chance to think about that. You have 4 forces, and remember, a force is really just a push or a pull, right? 4 forces acting on something, no acceleration. I'm going to go here and then go back this way. Yeah, go. Does that kind of make sense? Is that what you were going to say too? Oh, yeah. What were you going to say?
I was gonna say like four-way tug of war.
That's what yeah. That's kind of, that's where my brain was too, right? Like a four-way tug of war. So you've got like this thing in the middle, like some sort of prize, and then you've got like four teams like pulling, and right? Does that make sense? Could you have an acceleration of 0 with only 3 forces?
No.
Yeah.
Maybe. Yes.
It's one of the 3. It's either yes, no, or maybe, Zach. Good job. He likes to cover his bases because he doesn't like to be wrong. Have you noticed this? All right, so let's think about this and make a commitment. Yes?
Yes.
And I'll tell you the answer is not maybe.
Okay. Yes.
There is a definitive answer. Can you have
What else would be right?
something with an acceleration of 0 with only 3 forces acting?
Yes.
Sure. What can you think of, Anne-Marie?
If one person is pushing on one side and 2 people pushing on the other, but the other person is trying.
Sure, absolutely. So you've got 2 people pushing on one side, 1 person pushing on the other side. We could have a net force of 0, right? They could add up, and the acceleration of the thing could be, does that make sense? What if they were pushing from different directions? Could you have 3 things pushing and an acceleration of 0?
If you're in like a
Yeah.
triangle shape.
Yeah, like maybe they're not sitting like right on the axis, right? Like if you have a situation, just kind of thinking out here, if I kind of draw a picture, right? So here's my object. I have a person pulling this way, and a person pulling this way, and a person pulling this way. Is it possible that that object isn't accelerating? Sure. But if that's the case, what would you know about these 3 forces?
Equally strong.
They have to be equal. What if they were angled differently? What if, like this one was pulling like this? Are they necessarily equally strong?
No, not anymore.
Not necessarily. But what do you know about these things? What do they have to add up to?
0.
Does that make sense? They have to add up to 0. Now, you are all brilliant. Because if you weren't brilliant, you wouldn't be here, right? Yeah, that's true. It's true. I know. Yeah. But is that something that you have to be really brilliant to realize? That you could have 3 people pulling at different angles, and as long as they add up to 0, it wouldn't go anywhere? Does that make sense? Like, is that more or less a common idea? Like, you could convince somebody who you might not consider brilliant that that is true? Yeah? Okay, so let's write this not so brilliant but still important thing down. If the total, the resultant, we gave it another name last time. Do you remember what the other name was that we called it? The net? The net force? If Fnet is equal to 0, in any case, regardless of where the forces are pulling, if the net force is equal to 0, what do you know about the object? It's not what? I heard it, but say it loud.
It's not accelerating.
It's not accelerating. Is that okay? Could it be moving? It could be moving. I'm going to put that in parentheses because that's important. But it could be moving. We just know that if it's moving at a what? Constant rate. Does that make sense to everybody? Okay. So if the net force equals 0, then we know the acceleration is 0. That's not that, like, mind-blowing of an idea, I don't think. Let's take the other situation. So we're going to write it down. If Fnet, well, the opposite of being 0 would be that it is not 0, right? Like the other option. Zach knew that because he always knows like the 2 options to cover all of, right? Yeah. Like he's the Venn diagram guy that like covers everything. I got it all. I got it. Yeah. If Fnet is not 0, what do you know? There has to be, right? If we take a look back at our situation here, the situations where, like if we add these three forces together, do they add up to 0? No. Do they add up to 0 here? No. So what do you know about the object? It's going, and not only is it going, but it's going what? Or what's it doing? It's accelerating. It's speeding up or slowing down, right? It's changing its velocity. So let's write that down. Is that okay? I'm going to put in parentheses, can be speeding up, slowing down, or there's one other case. What else could something be doing if it's accelerating?
Changing direction.
How did you come up with that? Where does that come from? I agree.
The other thing, the direction.
Woo! He's got it. Yeah. It's the direction, right? Because velocity is a vector, right? So it could be speeding up, slowing down, or changing direction. So it's a cause and effect kind of thing. If there's no net force, no acceleration. If there is a net force, there is an acceleration. That's all there is to it. Is that okay? Right here, friends, this is Newton's first and second law. You've memorized it a bunch of times, but I told you to forget it, so you probably have forgotten already. And that's good. Because I want you to know this. This is good, logical stuff. You don't have to be the inventor of calculus to come up with this. Right? We got this. No problem. On a Tuesday morning, it's even dreary outside. Like, it might not be our, sharpest day, but we still get this, right? This is not deep and scary. In most physics textbooks, this would be called, as I just said, Newton's first and second laws. Oh, yeah, I just get really excited about second, huh? Thank you. First and second law, and usually it has an S because it calls it two separate things. I have a very strong feeling about this. It's the same statement, right? If this, then this. If it's not, then as Zach would know, it's not, right? Like, we get this. Are you with me there? So this is really just one law, one obvious statement. The only reason we call it Newton's is because he's the one that wrote it down. And he was very, very much of one of those, look at me, I'm so cool. I'm not a big fan of Isaac Newton. He was not a good guy. He was really not a good guy. You guys you did character count stuff when you were in elementary school, right? Yeah, the pillars of character. Isaac Newton would not be on a poster for that, okay? He was bad in a lot of ways. So he came up with a lot of things and then would refuse to publish them for a while, and he wrote somewhere, I read something that he wrote. He's like, I'm the only one in the world that knows this, and I think that's cool. What is that? That is so rude. You know what I'm saying? I just have a problem with that. He also had, I'm going to get on my little Newton rant for just a second here. There was a time when he was the head of what they call the Royal Society, which was all of the crazy smart sciencey people in England. And then there were Royal Societies in all of the other countries in Europe. And he was the head of the Royal Society in England, and he was doing all of this developmental work, and there was this other guy who he didn't really get along with that was doing the same stuff. And he didn't like the other guy, and so he kicked him out of the Royal Society and had his, because back in the day they had big portraits, right? So there are no pictures of this guy named Robert Hooke. Okay, I spent a long time online one day looking because I was teaching Hooke's law, and I was I wanted to, have his picture and da-da-da. There are no pictures because he had it destroyed. Kicked him out, was no, he didn't do it. That's just not nice. If you have an issue with somebody, deal with it. But don't, political, that's just bad. So anyway, Isaac Newton, not my favorite person. There are lots of things that he did that I'm not a huge fan of. He was pretty smart. I mean, if you're going to invent calculus, you have to be pretty smart. Okay, thanks. But you don't have to be, I mean, I'm not saying you guys aren't smart, but you don't have to be like a rocket scientist to figure this out. Are you with me there? Okay? This is not like mind-blowing stuff. You got it already, no problem. Okay? So, if you look at a book, it's going to say Newton's first and second laws. I call it Newton's first and second law, or just obvious, right? Like that would be another option to call it, okay? Now, there is one more little step that we need to take when we get here, when we're talking about this acceleration thing, because we want to talk about something like we want to talk about the acceleration of an object, I don't know, like an object falling, and not just say, oh, the acceleration's not 0, like we want to be able to say what it is, right? Not just that it isn't 0. So we'll talk about that, but we'll do that in a little bit. Okay? I'm going to put that off for a second. So maybe in your notes leave, I don't know, 5 or 6 lines here that we can fill in just a few minutes. Okay? Before we do that, though, I want to move on to a couple of other things because it just seems like a good time to do that. So I'm going to make a new page. You don't have to make a new page unless it makes you really happy. We have talked a little bit in drawing these pictures about some different kinds of forces. And last time that we were together, I told you about, well, I kind of broke some of your heads because I was making you upset about how we don't really touch things and all of that sort of deal, right? And I told you that there are these 4 fundamental forces, and then there's this contact force thing. And I told you that we really are just going to play with contact and gravity. I want to go just a little bit deeper and make a list here of the forces that we're really going to deal with. Okay? So last time we said that we were going to talk about contact forces and gravitational force. But I want to define those in a little bit of a better way. Okay? So when we're doing problems this chapter, and we're dealing with Newton's first and second law, and we talk about the net force, remember net is just adding up all of the forces together. I want to be able to figure out what forces are acting. So one of the forces that we'll deal with a lot is the force of gravity. And we'll name it. That's okay. We can call it the force of gravity. We mentioned last time that sometimes people call the force of gravity the weight of an object, and I just want you to make sure that you remember that you're okay with that. Okay? We are very rarely actually going to use this word weight, though, because I don't want you to get bogged down in it. Okay? What I want you to know right now is that the force of gravity is a force between, hey, how many objects need to be involved in a force? 2. It's always 2, right? When we're talking about the force of gravity, for this chapter, we'll get it, it'll get a little deeper later. But for right now, whenever we're talking about the force of gravity, we're really just talking about the force between the Earth and whatever object it is that we're discussing. Whether it's a frog or a bowling ball or a roll of tape or a water bottle or whatever. Okay? We can calculate the force of gravity. Okay? So it's the force of the Earth on something, but we can write it as F sub g. But it's always going to be a force between the Earth and some object. Does anybody know how we calculate the force of gravity that's acting on the frog or on you or on the bowling ball or anything? Have you seen that in the book yet? No, I haven't looked at the book that far yet. Okay. What's it dependent on? What's that? Acceleration, right? The acceleration of gravity, right? And we've known that, we understand that, we've been doing that for a long time. That's little g. And that's where the vector part comes from. Is it only dependent on the force of or the acceleration of gravity? No, because if it was, then we'd all have the same weight, right? Because we all accelerate down at negative 9.81 meters per second squared. Does that make sense? But I do not weigh the same as the frog. between the frog and I, besides the fact that he's pretty cute? His mass is different, right? The bigger your mass, the bigger your weight. Yeah. So anytime you're working on a problem, if you're given the mass of the object, you can very quickly and very easily calculate the force due to gravity or the force between the Earth and whatever object you're talking about. You just take the mass of that object, multiply by negative 9.81 meters per second squared, and that will give you the force. Is that okay? We're going to look at the units here. We kind of alluded to this earlier, but let's go ahead and kind of actually peek at them. What are the units of mass? We're not in chemistry, my friends. We're in physics. That's right. In physics, we use kilograms as our unit of mass. And what is the unit of acceleration? You got that, right? So the unit for force is going to be a kilogram times a meter per second squared, which is a really big mouthful. And because Newton was a really, really good PR guy, and everybody thought he was so great, and he did all this stuff with forces, very la-di-da, he got his name attached to kilogram meter per second squared, which I guess it's a little easier to say than kilogram meter per second squared, right? I weigh 17 kilogram meter per second squared, right? Like, you don't say that. No. You would say that you weigh a certain number of newtons, okay? Now, I just want, this is a little bit of an aside, but it's important. If you stand on a scale somewhere in the U.S., probably it's not going to be measured, the units are not going to be in newtons, they're going to be in what? Pounds, right? Pounds are the British or the English unit for Newton, right? It's kind of like inches and meters, or it's that kind of deal, okay? There's a conversion, whatever, we use pounds. Now, if you go to any other country besides the U.S. or England, and you ask somebody how much they weigh, I mean, I guess that would be kind of an awkward question, but you're having a conversation about how much something weighs, what unit are they going to give you and answer it? Kilograms. Are they really telling you their weight or the weight of whatever object? What are they really telling you? They're telling you the mass of the object. Does that make sense? Okay? So we talk about, in real life, we talk about the fact that pounds and kilograms are the same, but they really are not. If I have a 5-pound bag of apples, and I weigh it in Des Moines on a scale, it's going to say 5 pounds, right? If I take it to Thailand, and I weigh it there, it's going to have a weight of how much? 5 pounds, right? Okay? If I take it to the moon, because I, need the snack while I'm on the moon, and I put it on my scale on the moon, is it going to say 5 pounds? No. Why not? What's different? What's different?
Mass is affected differently on the moon.
You got to be very, very careful about your words. This is why we're talking about this. Is the mass different on the moon?
No, the moon has a different mass.
So what?
So has a different force.
That's true. I agree with that. It has a different force. And if I was going to calculate the force of gravity acting on the apples, has the mass of that bag of apples changed? No. Assuming I didn't eat one in transit, okay, the mass stays the same, but what changes?
The force of gravity acting on the
Careful, not the force, the force changes because what changes?
the gravity.
The something of gravity.
Acceleration due to gravity.
Yeah, there we go. The acceleration changes, right? The acceleration changes As Madison said, because the mass of the moon is different than the mass of the Earth. We'll get there, like right before summer. Okay, we'll talk about why that all works. But for now, you just know that the acceleration changed. Okay? If I take a scale at like a triple beam balance, and I balance it, and I have 3 kilograms worth of apples, and I measure the mass of my apples in Des Moines, and it says 3 kilograms, and then I take those apples to Thailand, and I measure it on a triple beam balance, what's the mass going to be? 3 kilograms. And I take my triple beam balance and my bag of apples, I didn't need any of them, to the moon, what's the mass going to be? 3 kilograms. Are you with me there? Mass doesn't change. Force of gravity changes. Okay? I'm going to give you 45 seconds to write down what you need to write down based on that little conversation we just had. Whatever resonated with you, whatever needs to stick in your brain, write it down. Okay. Do you have enough time? We okay? The last thing that I want to write down about the force of gravity is the direction. We should know the direction, but just so that we don't forget, what's the direction going to be? The force of the Earth, between the Earth and an object, where's it going to point all the time? Where's it going to point? Where's it going to go? Down. Yeah. Goes down towards the center of the Earth. Always towards the center of the Earth. We're going to write that down because it's important. It always points toward the center of the Earth. Issues or questions with that? Okay. One force down. There's one more I want to talk about real quick, and then we're going to do some problems. The next force I want to talk about is, well, it's got kind of a funny name, so I want to wait on the name for just a second. I want to go back here to this picture. This thing right here is what kind of force? The Earth on the ball, that's what kind of force? Gravitational. That's the one that we just talked about, right? We've also got this thing, the floor on the ball. And I don't know if you remember last time that we were together, but I put the frog maybe on right here. And if I was going to draw a free body diagram, oh yeah, that's where we draw all the forces, right? If I draw a free body diagram of that frog, what would you say besides the Earth on the frog? Books on the frog, right? And if I put the frog right here, then you would say what? The cart on the frog. And if I put the frog right here, you would say the table, right? There's like something, some sort of surface pushing up on the frog. Does that make sense to everybody? Okay, so I want to talk about that surface force. It's got a kind of a funny name, but it's a very important name, and it's very indicative of what is going on. You guys know the word indicative, right? Have you heard that word before? It's a good word. It indicates what's going on. That's what I'm talking about. Right? That's a good word. Indicative. Word of the day. There you go. All right. This force is called the normal force. Now, I don't know why, but a lot of people have a hard time with that. And let me see if I can help make it so that you all don't have a hard time with it. You've heard the word normal before, right? There are two very different definitions. If you look up the word normal in the dictionary, normal. One of them is going to be what? What does normal mean? Ordinary, right? Ordinary, plain old, regular, not spectacular, right? It's been a very normal day. Okay. That is not what this normal means. Okay? Have you heard the word normal in any other context? Maybe in a math class? That's where I've heard this version of the definition of normal. Has anybody heard the word normal in math class? Where have you heard it? Like, we probably talked about it last year.
Oh, like the
on.
Well,
There's another. What's that?
like,
What did you said something?
if you talk about it, that's the first thing.
What did you say? What?
So like when you talk about shapes, it's like the standard.
Okay, so that's this definition too. Maybe you haven't heard this word. So maybe I'm going to teach you 2 big words today. 2 important words. So we had indicative. That was a good word. This one is one that you will use a lot. I promise you'll see it in math. Maybe you just haven't encountered it yet. I don't know. The word normal, besides meaning regular, plain old, the standard, the regular, the unexciting, the unextraordinary, also means perpendicular. Have you heard that before? Okay, if you haven't, now I'm learning you. It's a good thing you came to school today, right? All of these things to learn. The word normal means perpendicular.
Like this?
Like this. 90-degree angle. Okay? The reason we like the name normal for this force is because instead of always pointing towards the center, this force is always perpendicular or something. Perpendicular to what? Well, let's talk about that. That's kind of important. The normal force is always going to be a force between a surface and an object. So it could be a book, it could be a table, it could be a cart, it could be the floor, it could be a chair, it could be your hand, it could be a ceiling, it could be anything. A wall, but it's always a surface. It's a force between a surface and an object, and it always acts perpendicular to that surface. Okay? Always, always, always. Now here's the fun thing about the normal force. You know, when we were talking about the gravitational force, we had an equation for it, right? Like, boom. You know the mass, you know the gravitational force, you're done. Normal force doesn't work that way. The normal force varies. What? It changes. What? Depending on the situation. That's weird, right? So the magnitude, you guys know what I mean when I say magnitude, right? What does magnitude mean? The quantity, the size, how much. The magnitude of the force varies depending on the situation. That doesn't mean that it varies like as the frog sits on the table, okay? But it means that it varies depending on how many frogs are sitting on the table. Let me give you perhaps a practical example. I found it to be pretty practical when I was thinking about this. How many of you have the job or have had the opportunity to help put away dishes at your house? Have you ever had that opportunity? Yeah, some of you are like, how did I miss out on that? I'm sure that if you offer to whoever actually puts dishes away, they'd be like, sure, we'll let you help. Okay, so I want you to imagine a situation where maybe you and a parent or you and a sibling are putting away dishes, maybe emptying the dishwasher or taking them from wherever they are. You put your hands out and somebody puts a plate on your hands. Can you imagine that? You can't picture that? Try really hard, Everett. I bet you can. Imagine this. So somebody puts a plate on your hands. Now, assuming that you're not being really ornery, assuming that you're not trying to break the dishes, would you agree that the goal here is for the acceleration of that plate to be 0? Okay. If the acceleration is 0, what do you know about the net force? It's 0, right? So that means that if you've got, so we'll draw a little picture of a plate here. So there's my plate, and there's a force from the earth pulling down. Oh, I was going to say ball, but it's not a ball, it's a plate. And then there's a force of your hand on the plate, right? Plate. There we go. Okay? Now, what if somebody puts another plate on top? If you push with the same force that you were pushing with before, what's going to happen to those plates? What's going to happen to them? Somebody raise your hand and tell me. What's going to happen? I don't want to talk to Zach anymore because he's talked a million times already today. What's going to happen to the plates? I've talked to you a bunch already. Come on, friends. There are a lot of you that haven't talked yet. What's going to happen to the plates? If you're not paying attention, this has happened to me before. Like you're talking to somebody else, somebody puts another plate on your hands, so you're just pushing up with the same force that you're pushing up with before. What happens to the plates? Like even maybe just briefly, what's going to happen, Rowan? Yeah, they're really good at, right? You're like, whoa, and then you have to like react to that. Does that make sense? Yeah, they would, if we talk about it in terms of physics, they're going to accelerate. Are you with me there? Downwards a little bit. Whoa, okay. Until what? Either they crash to the floor, or what? You catch them, and you apply a force that's a little bit larger than it was before. Are you with me there? Okay. So they put another plate on your hands, which means that the force of the earth gets bigger, so now it's like twice as big. And so when they put this plate on the second plate, then the force that you apply has to be equal to this, twice as big as it was before. Are you with me there? Then they could put another plate. Oh my goodness. They put a third plate, so now it's times 3, which means that your force has to be, it has to be even bigger, right? 3 times as much as it was to start with. Are you with me there? So if you've ever had this experience where things get heavier and heavier and heavier, and you have to apply more and more and more force, that's what this is. That's this normal force thing, okay? You are trying to avoid the plates. You're trying to avoid a situation where the plates accelerate downwards. So you're trying to push up the same amount as gravity is pulling down. Is that okay? Okay. I need everybody's pencil to move. I want you to write that down so you don't forget. I'm going to give you 30 seconds. I want everybody's pencil to move. Explain that to yourself. Write down the plate thing, or write down something like it so that you remember what we just talked about.
Then the force on Earth is the normal force, or is it having them both equal to, or having them equal 0? Is that the normal?
Yes and no. It's not always going to be exactly opposite of the force of the Earth. Okay, and we're going to do a couple examples that will show you that in just a minute, okay? The normal force always tries to avoid acceleration. Is that fair?
Yeah.
So the normal force is always acting to avoid the object from accelerating perpendicular to the surface. That might be a good thing to write down. I might write that down too. Okay? So the normal force acts to prevent, maybe that's a better word, an object from accelerating perpendicular to the surface.
Could it also be like someone holding something down?
So usually, like, okay, so if I had a book and I was pushing down on it, and we're going to do a problem like this in just a second, then I would call my hand just an applied force, but the normal force from the table would be bigger now, right? Because it's trying to prevent this whole thing from accelerating downwards. Does that answer the question you're asking? Okay. All right. I think this will all make more sense if we can try out some problems. So, here we go. I said it was pretty simple. I said that Newton's first and second law was not a big deal. And it really isn't, but there are some steps that help us to actually solve the problem. The harder part is getting the net forces figured out. But we've got lots of time. We're going to figure it out right now. So here we go. I've got 3 problems for us to work on. We might get through all 3 of them today. We'll kind of see. We'll figure it out. I want you to ask questions. I want you to understand this stuff, okay? The more that you're engaged with me now, the easier the problems are going to be for the rest of the chapter, okay? I promise. I've been doing this for a while, and this is what I found to work pretty darn well, okay? So, we've got a situation with a frog sitting on a horizontal surface. Oh, like it is right now, right? Yay, he's like, what a good frog we have, okay? The question asked, or the task, asks for you to determine the normal force acting on the frog while he's sitting on that horizontal surface. Well, is there an equation for normal force? We didn't write one down. So we need to figure out a way to do it. Okay? I'm going to walk you through this one. I did put this up at the very top. For each problem, draw an FBD. What does FBD stand for?
Free body diagram.
Yeah. So that's the diagram that has all the forces acting on one object. And write an Fnet equation, or equations. In this case, we just need one. So here we go. We're going to do it right now. You do it too. If you just want to write normal force problems, then you can always come look at this again to figure out what the problems are. Here we go. We're going to draw ourselves a free body diagram of the frog. I'll let you do it, and then I'll compare with you in just a moment. Go ahead and do it, and check with your neighbors once you've got something drawn. Really okay to talk to each other. Have a conversation. Talk, talk, talk. I have a picture. What does your picture look like? Oh my gosh, it looks like my picture. So I really, really want to talk to new people. There are some of you that are loud, and that's cool. There are some of you that are quiet, and that's cool. But I bet that even my super quiet friends have some answers that they would maybe be willing to share. I'll give you an opportunity here. I've got a frog. I need to draw some forces on him. Raise your hand if I haven't talked to you lately. I talked to you, or I have talked to both of you guys. I want to talk to somebody new. I can start calling on people, but I don't want to make people uncomfortable. Has everybody talked to their neighbor so they have something to say? Yeah? Put your hand up in the air. Be bold. Be brave. You can do it. You can do it. Yeah, Skylar, what you got? What's a force acting?
The earth on the ball.
The earth on the front. That's perfect. And which way does it go?
Down.
Down. How many of you agree with Skylar? Do you have a force going down? Sweet. Let's do it. I'm going to add it because I want to be cool too. So the force of the earth on the frog. I'm not going to grade it wrong if you say it's on a ball or on an object, whatever. I want the earth part there, though. That's important. Any other forces that you had acting on the frog? What else did you write down? Yeah, what you got? And which way does that one go? Up. And you know it's up specifically because it's what to the surface of the table? Perpendicular. Yeah. So we've got a force like this. So this is the force of the table on the frog, or the surface, or the whatever. Okay. Did anybody have any other forces acting on the frog? Okay, cool. All right, so we've got our Fnet, or our free body diagram drawn. Now we're going to write down our Fnet equation. This is the key to everything, my friends. Right here. Free body diagram allows you to write an Fnet equation. Do not try to write an Fnet equation without drawing a free body diagram. It doesn't work. You always miss something. Okay? Free body diagram, Fnet equation. So Fnet equation just means what forces are acting. That's all we want to know. Now, once I have the free body diagram, I'm just going to write down the forces. So I've got the force of the table, and I'm actually going to put in parentheses here, the force of the table is what kind of force? We got two choices right now, gravity and normal. Normal, right? I'm going to call it F, and I'm going to put that in parentheses on my free body diagram. And so I'm going to write F sub n here, just to make my life easier so I don't have to write so much stuff out in my net force equation. Is that okay? And then what else am I going to write? Force of gravity, because my other one is an FG, force of gravity. Are we doing okay? Is the frog accelerating? He's just sitting there. His velocity's not changing, so he's not accelerating. If he's not accelerating, what do you know about his net force? Has to add up to 0, right? So I'm going to say Fnet also equals 0. This thing here, this Fnet, really just allows you to write the rest of it. Really what you want to look at is this part over here. Okay? Those two things have to add up to 0. What do you know about two things if they have to add up to 0? Opposite in direction, right? And what about their magnitudes? Equal in magnitude. Is that okay? So I'm going to write this out a little bit more. These little vector hats that I've got up here mean that we're talking about directions. Fn goes up, so I'm just going to write Fn. Fg goes down, so I'm going to write minus Fg equals 0. Is everybody okay with that? Yeah. See, okay, so this is the game, and this is like the big deal, so I'm glad. I was hoping somebody was, thanks. High five for asking that question. I appreciate that. Because I put my negative sign and my imaginary positive sign that doesn't really appear there, I don't need my vector hats anymore. Does that make sense?
Yeah.
If you are doing this and you write vector hats here, I'm not going to count it wrong. Okay? But technically, this would be the right way to go. And then I can subtract Fg from both sides. So I've got Fn is equal to Fg. Do I know how big Fg is? I can figure it out, can't I? Because Fg equals, what was it? I don't remember. Boom. Mg? Is that okay? So we can say that Fg is equal to Mg. I've already taken the negative into account, so I don't need a negative sign anymore. I know the mass is 0.45 kilograms. I know the acceleration due to gravity is 9.81 meters per second squared. And based on that, with the calculator out that you have out, you can tell me the normal force. So go ahead and calculate that real quick. Just a nice little multiplication problem then, right? That's not hard. Want to make sure everybody's got it. So once you've got it, check with your neighbor. Make sure it makes sense to them. Make sure it matches what you have. How are we doing? Are we doing okay? Hey, Maggie, can I pick on you for a second? She's like, I don't know. All I want to know is what you got. What did you get for an answer? 4.41, she says. Do you guys agree with her?
Yeah.
Oh, that was not resounding. Do you not agree with her? You think she's, I think it's okay. Yeah, 4.4. She said 4.41. Were you upset about the 1? Why were you upset about the 1? Because of sig fig. So I'm not going to freak out. But that's the only reason. And then what are the units? Newtons, or if you're really anti-Newton, you know, kind of like me, then you could write it as kilogram meter per second squared. But as much as I dislike Isaac Newton, I am also lazy. So I'm going to write it as 4.4 newtons. How are we doing? Is that okay? Yeah. Okay. Question number 1 done. 2 more to go. We'll get done at least with number 2. We'll see how we do. We can always come back to them on Thursday. All right. Before I move on, any questions about this one? Anything that didn't make sense? You're going like, why did you do this? Or, yeah.
Is the Fn, is that, what is the Fn again?
What is so F is force, and the N stands for normal. Yeah, it's this thing here. Does that make sense?
Yeah.
If you are more comfortable writing this as just the force of the table, You can do that. Yeah, that's fine with me. It doesn't bother me. Whichever way makes more sense to you. Any other questions before we move on to the next one? Yeah?
Why did you go, if you had Fn plus Fg equals 0, why did you go from that to Fn?
This one? Well, if I have two numbers and they add up to 0, I know one of them has to be negative, right? And so this was really just articulating then which one was negative to make sure that I'm not crazy. If I had two forces that were both pointing up and no forces pointing down, would it be possible for me to have a net force of 0? No. So it's really just articulating more clearly what's going on here. Does that answer your question?
Yeah.
Okay. Anything else that I can answer before we go to the next one? Everybody always laughs at the next question, but I don't want you to laugh because, I mean, if you take care of your animals, then you probably need to take them on a walk. So I'm going to take the froggy on a walk, which means he needs a little leash. So I'm going to put a little leash on him. He likes to go on walks. So he thinks it's pretty fun. And so here he is. He's got his little leash, and he's going to go on a walk. And so he's walking like this, right? It's kind of, it works. Okay, now, while I'm walking with him, I'm walking and he's moving, but he's moving at a fairly constant rate. Is that okay? If he's moving at a constant rate, then what do you know about the net force acting?
It's not 0. Is that what?
Let me say that again. If I'm moving at a constant rate, he's moving, right? We all agree. His velocity is not 0. Is his acceleration 0?
Yes.
His acceleration is 0. Does everybody agree with that?
It's not going fast.
He's not speeding up or slowing down. What do you know about his net force? That it's what? It's 0. It has to be 0. If he's not accelerating, then there's no net force acting. Is everybody okay with that? Okay. Is he accelerating in the up and down direction?
No.
Certainly not. Not in this. Not right now. Watch. Can you see? Come on. Like he is not accelerating the up and down direction. Okay? Is he accelerating in the x direction?
Yes. No, wait. What?
Not when I'm moving at a constant rate.
No.
Constant rate. Constant rate. No. Okay.
No.
So. We really only care about the normal force for now. So here's the question. This question, or this task, I guess, asks you to determine the normal force acting on the frog who's being walked along a horizontal surface with an applied force. Applied force? What's that about? That's me pulling on him, okay? A force of 2.5 newtons at an angle of 65 degrees relative to the horizontal. Before we do anything, I want you to think about it for just a minute. Is the normal force going to be the same as it was in the first question? That's an interesting question, Ms. Carveling, right? Is the normal force going to be the same as it was in the first question? What does your gut say? Raise your hand if you say, yes, the normal force will be the same. What does your gut say? No, the normal force will not be the same. You can put your hands up, it's okay. Believe in yourself. If your gut feeling says, I'm not quite sure what normal force is, or I don't really know, raise your hand. Everybody's got to raise their hand at some point. Zach would tell us everybody had to raise their hand at some point there, right? Yeah? I don't know. I have no idea, Ms. Carveling. Why are you even asking me this question? Help me out so I understand. Is that how you're feeling? Yeah? Okay, let's do it. Here we go. The very first thing we're going to do when we're trying to solve any of these problems is what? A picture. Not just any picture. A very specific kind of picture. What kind of picture? A free body diagram. So I've got my frog. Let's talk about the forces that are acting on him. Raise your hand if you can tell me a force that's acting on the frog. I'm going to wait for my friend. Yeah, go. What you got?
The force of gravity.
Force of gravity. The force of the what acting on the frog? What would you call that?
Gravitational force, or the
I want to go buy something from the store, though. What is it going to be? What's that object?
Earth.
The earth. Yeah. Okay, is everybody okay with that? So I've got the force of the earth on the frog. And then in parentheses, I am going to write that that's the force of gravity. But I want you to have both of those things written down. What other things do you have acting on the frog? What else is acting on the frog? What else?
The force of the floor on the frog.
The force of the floor, the ground, or the whatever it is that I'm walking him on, right? Where does that one go? Where does that one push? Yeah. Up, is that what you said? Yeah, up. Perpendicular to the surface. So here is my surface, right? And it's going to push up perpendicular to the surface. So this is the force of the floor on the frog. Cool. Are there any other forces acting on the frog? Sean Anderson, what do you see?
The leash.
The leash, right? That's the whole point of the, right? There's the leash acting on the frog. And it's acting at an angle, it says. So I'm going to go ahead and draw like a right there. And it says at a 65-degree angle relative to the horizontal. And we are experts from chapter 2 or chapter 3 on this. So we know that it's going to look something like that. And that's the force of, he said, the leash on the frog. And because it's not anything else that we've talked about, I'm going to call that just an applied force. That's kind of like my basic answer for anything that's not anything we've specifically talked about before. Are we okay there so far? Because this force is acting at an angle of whatever it was, 65 degrees, can we break that into two pieces? Like one that's acting in the x direction and one that's acting in the y direction. Are you with me there? Is that okay? Yeah. I've got one that's going over like this. I'm going to call that FA. It's just like that homework problem we were just talking about. FA sub x. And I've got one that goes up. I'll call that FA sub y. See how this all fits together? Like it's good that we did chapter 3 before we were doing this, right? Like I wouldn't know how to do this if I hadn't done chapter 3 already. If I want to know the net force acting in the up and down direction, that means I'm just going to write down all the forces that are acting in the up and down direction. Can we do that? Okay. So here we go. We're going to write Fnet. And just to clarify, I'm going to go ahead and write that that's in the y direction. The y being in the up and down direction. Just going to look at my free body diagram and say, what's acting in the y direction? I want you with your partners to see if you can just write down whatever is acting in the y direction. Talk to them real quick. Write them down. I'm going to pause for like 20 seconds. I want to give an opportunity to my quiet friends to tell me something here. You've had a minute to talk to your neighbors. So you've got something out there. Can I pick on you, Ashley?
Sure.
Sweet. Can you tell me one of the things that goes on that list?
The earth on the frog.
The earth on the frog, right? The earth on the frog is acting in the y direction. Would you agree?
Yeah.
How many else of you had that earth on the frog? I think so. Absolutely. I'm really lazy, so I'm going to write that as FG, but you could write F the earth, and that's totally fine as well. Both of them are correct. They're the same thing. I'm going to pick on some other people if I can. Emma, can I pick on you? Am I allowed? Is that okay? Did you have anything else written down? F-A-Y, because it's labeled with a Y, right? So it's got to be in the Y. Yeah, absolutely. Yeah, F-A-Y. Fantastic. Anything else acting in the Y direction? Yeah, Cindy, what you got? The floor on the frog, absolutely. And I'm going to be lazy, so I'm going to write that as the normal force, but you can write that as floor if you want. Either way is fine. Anything else acting in the y direction? Did you have anything else? No. Is the frog accelerating in the y direction? No. No. If he's not accelerating, what do you know about the net force in the y direction?
0.
It's 0. So I'm going to set that equal to 0. Look at that. And then I'm going to remember that this is the part that I really care about. That Fnet is just there to kind of help me. Okay? And now let's solve for Fn. I'm going to go one step at a time and say, where are they pointing? Are they going up or down? Fg, is it going up or down? Use your thumb to show me. Up or down? Fg is going down. It's going to be negative, right? So I'm going to say negative Fg. Fay, is that one going up or down? Use your thumb to show me. Or your finger if you want to be weird and crazy. Or 4 fingers, or I don't know, your eyes or your nose or what. It's going up, right? I don't know. You guys are weird sometimes. What about Fn? Fn, is that one going up or down? Indicate to me. Up, up. Are we okay there? Let's get Fn all by itself. Since it's positive, I'm going to leave Fn and I'm going to move everything else over. Is that okay with everybody? Okay, so I'm going to say Fn. I'm just going to move it over a little bit just so I don't run out of space. So that's going to be, so the Fg is going to turn positive, and Fay is going to turn negative when I move it over to the other side. Is that okay, algebra-wise, for people? Okay. Do we know what Fg is? Yeah. I mean, you could say that it's Mg. You could also say, hey, wait, we already figured it out in the last question. It's 4.4. Either way is okay with me. Do you know what Fay is? Can we figure it out? So here's Fay. You know that this is 2.5. You know this angle is 65. How do you figure out what Fay is then? Yeah. Perfect. So that's going to be 2.5 sine of 65. Before you go today, I want you to figure out what Fn is. Do that really quickly for me right now. Check with your neighbors, see if they agree. If you need help with something, if it's not making... Did you get an answer? Mitch, did you get an answer back there? What'd you get? 2.1 newtons, he says. Do you guys agree with him? Okay. So, before you go, hold on, stay with me. I have 2 things you need to know. One of them is very important. The other one is I just want to make sure it makes sense. What happened to the normal force? Did it get bigger or smaller? Smaller. It got smaller because there's something else pushing up. Okay? This is the thing you really want to know. On your homework for next time, 20, 23, 26 are doable, but you need to make sure you read the book. 28 and 29 we have not gotten to yet. You may skip those for now, but they will be due then the next time. Does that make sense? Yeah. So you may skip the last 2 questions on the homework. They will be due, just not next time because we haven't gotten there. Okay? Have a great day, guys. I will see you on Thursday.